Okay, let's begin. Questions on chapter 1. Let's start with 1.1. Let's quickly get through this.
Like, did we just give you questions?
Yeah.
Just go to question 18.
15.
18? What?
It was e to the e Harvard to the negative, and then that's the negative t Harvard.
What is that asking you to find the derivative? So why was this and they asked you to find the derivative?
Yeah.
Okay. Y prime equals.
Same thing.
Yeah, well, we know it's going to be the same thing times
Derivative
the derivative of the power, right? Now look at that. What's the derivative of that?
e to the negative t.
Same thing times the derivative of its power. So it's end up going to be minus e to the minus t times e to the minus t, which you may simplify as e to the minus t minus t. So it's just a double application of the chain rule. And we're using the rule d dx of e to the u is u prime e to the u. You applied that twice. Other questions? Someone said 15, I think.
15. So ln of parentheses e to the x squared plus 1. And then we find the derivative of that.
Okay, so y prime equals
1 over e to the x squared plus 1 times the derivative of that.
Times the derivative of
So
this.
it's e to the x squared times 2x. And then the derivative of that.
Derivative of what?
That's it.
That's it.
That'll just be it.
Oh,
Alright, derivative of this is that. Derivative of 1 is 0. So that's it. 2x e to the x squared over e to the x squared plus 1.
Yeah.
No simplification there.
No?
Nope, what can you do? Oh, cancel.
Yeah.
Try that. There's a plus sign here. Can't cancel, can't simplify. That's it. Yeah.
Oh.
What?
it's a
That's, is the negative still in that answer? I just wanted to clarify.
Yes, the negative is
Yeah,
for
it's still there, right? Yeah, okay.
See who's paying attention. 37?
Yeah, it's the integral of e to the x plus e to the negative x over e to the x minus e to the negative x dx.
Okay. Ideas?
You submethod?
Right, it's not a basic rule, so what do you substitute? The bottom, because the bottom is what makes it complicated. What, just the top, no problem. The bottom makes it complicated, let's try doing that. Let's check, it's a good substitution. Find its derivative, we get to the x plus e to the minus x, right? Because derivative of this is minus e to the minus x, makes that minus a positive.
Times dx.
Dx. It's right there. So then this guy would just become 1 over u du. Integral of 1 over u. ln u plus c equals ln of
Number 12.
and the absolute values is necessary for that one because that inside can be negative at some point. So that's not a formality. What is it?
Number 12 is 1 divided by 1 plus 2e to the negative c.
Okay. What are we doing?
The derivative.
Okay, so how do we do this one? To rewrite it, right? 1 plus 2e to the minus t to the minus 1. Now just apply the chain rule. Negative?
1 times 2e to the negative 2 to the negative 3 times 2e to the negative 3 times negative 1.
Yeah. Negative here would cancel the negative there, so I just have 2e to the minus t times 1 plus 2e to the minus t to the minus 2. We're going to do the whole thing. Square root of x plus 1, like that?
Yep. Belongs to the fourth power. Divide by square root of x. Everything over that. dx.
Okay, ideas?
Can you write it first? You can bring up the.
Right, so it's a fourth power. It's possible to expand, but I probably wouldn't want to. Even though I could.
Radical x plus 1.
You could do a U-Substitution.
Yeah.
du would be
1
1 over
1 over 2 radical x dx. I can multiply by 2 to get 1 over radical x dx. And you're like, here it is.
Did you do 24?
We're not done. So here, if I write 2 du, it replaces all of this. And I'm left over with this guy to the fourth, but that guy's my u, so that's just u to the fourth. And how do I integrate that?
2 to the fifth over 4.
Yeah, power rule. Radical x plus 1 to the fifth over 5. 21,
24.
24.
It was parentheses e to the 2x plus e to the negative 2x. Parentheses.
Huh?
Yes, the derivative. Integral.
That's it?
Yeah.
Okay, what's the problem?
1 over 2
It's the 1 on
2x minus 1/2 e to the negative 2x plus c.
Right, those are basic rules. You don't need a substitution of anything. Last time we learned that e to the kx dx is 1 over k e to the kx dx. There's nothing to do here.
Oh, can you go over 25, please? Sorry, 29. This integral sign, x plus 1 over x plus 2 dx. And you're supposed to divide x plus 1 with x plus 2.
Didn't we do this problem already?
Yeah. But I didn't understand. I have the steps written down.
It was the other way around. It was like 1 plus x over
Yeah,
x
it's 1 plus
2.
x.
But this is a
You
little
did
different.
It's the
division
same
into
thing, but
it,
still.
and I couldn't divide x plus 1.
You added 2 and then subtracted 2.
That's
Division
all.
was one way to do it, if you want to do log division.
That's
I just try to get the denominator in the top.
Yeah.
X plus 2 minus 2. This gives me x plus 2 minus 1 over x plus 2. In which case I'd split this up. X plus 2 over x plus 2 minus 1 over x plus 2. This cancels. So that's just the integral of 1 minus 1 over x plus 2. Integrate this, x, integrate this.
ln of x plus 2. see.
You could have done long division, and long division would have taken you here. And then do that. Okay, that's it. Pass your homeworks up to the front. And we will continue with chapter 2. Do a little bit more on ODEs. Not all of them? Yes, sir. Okay, so last time I talked about a particular kind of differential equation describing a particular kind of situation. So, recall P at time t is a quantity that grows proportionately to its current size, compounded continuously. Regular constant change k is described by p dt equals rp plus k. We're going to apply this directly to money, but it also applies to many other situations like populations. Populations would follow a similar model, some populations. Okay. So what was R in our situation?
It was a percentage written in decimal.
0.05.
Oh,
Right. Let's look at in the money application. We'll talk about population application. It's interest rate as decimal percentage. If it's a population, it would be the percentage of growth that it's experiencing. K would be
like
it's a constant value, but what's important about it? Huh?
The actual
depends on time.
Constant, right? Amount
Driving up D changes.
being withdrawn or deposited. How often? At regular time intervals. Right? Every month, every year, every day, some sort of unit of time that we will talk about later.
Isn't that the initial amount that we have?
No, initial amount is P naught, right? So there's an additional piece of information that you've been given. You're given P equals P naught is an initial condition. This is the initial amount. Right, so that's an extra piece of information you can get. And the initial amount, the differential equation just describes the rate of growth. This is the rate of growth. How fast is this thing growing is described by this equation. So if I know the interest rate and I know how much I'm depositing or withdrawing per unit time, I can tell you how fast the money is growing, provided it is being compounded continuously. So I keep adding interest and then charging interest on the new total, and I add interest again, charge interest on the new total, and that keeps happening in such a small period of time that it's indescribable. Okay, so that's where we were. Now we're going to use this idea to solve some problems, see how we can apply these guys. And last time I actually solved two ODEs. Right? We learned where the PERT formula came from. It's actually when k is 0, and you go through the solution, you get the PERT formula that they told you about in 205. We also solved this one in general, which gave you a slightly more complicated formula, but it's a far more general formula than the PERT formula. The PERT formula assumed that nothing was being added or subtracted in a regular time interval. So let's see what an example of a problem might look like. You deposit $1,000 into an account. Completely fictitious account, grows at 5% interest rate. Per annum, compounded continuously. A. Right, an ODE with initial condition to describe this situation. B, I want you to solve this ODE. Then I want you to tell me, how long will it take to double your money? And more than that, how much money will you have after 6 years? Let's start with A. Describe this as an ODE with initial condition.
dt over dt.
EDT. Okay, so far so good.
0.05,
0.05, where did you get that from?
the 5% interest.
5% interest rate. R is the interest rate as a decimal percentage, right? 5% as a decimal, you get 0.05.
Nice b.
E, right, which is the function, so function of time,
Plus K.
Plus 1,000.
plus 1,000.
Plus K.
Plus k.
We don't know K.
Is 0.
K is 0, right? I was not told that I'm going to be continually putting money into this account. I put in $1,000 one time.
Oh,
There's no continual deposit or withdrawals being made, right? It's not just a deposit or withdrawal, it's a deposit or withdrawal at regular time intervals. It is a repeating process.
so
Okay, so K is 0 here. Now what? We're not done. I also want an initial condition. What's the initial condition?
then you start off with 1,000.
How much did I start with? 1,000. Right? So this guy's the ODE. This guy here is my initial condition. Okay. That does it for part A. Part B says I need to solve this ODE. How do I solve this ODE?
You just cross multiply.
So I have dp over p equals 0.05 dt. Now what? Integrate both sides. Integral of this side. P. Integral this. C. You need to solve for P and exponentiate both sides, so you get P is equal to CE to the power 0.05t. Are we done? You have to plug in. I was given an initial condition, which means it's not good enough to have a general solution where the C is. I need to find that C. So I know that P of 0 equals 1,000. This means that when time is 0, the amount in the account is 1,000. So I plug in 1,000 here equals CE to the 0, which means that C is 1,000. And hence, the amount of money I have in the account at time t is 1,000 e to the 0.05 t. And that is part B. Part C, how long will it take to double your money? How do I figure that out?
I have it there. Would it be like 2,000 is equal to P?
Yeah, 2,000 must be equal to what? To that thing.
Yeah.
Right, so 1,000 e to the 0.05 t, which means divide both sides by 1,000. 2 is equal to e to the 0.05 t.
Jhevon, I have a question.
Yes.
For B, if you don't want to go through that process, can we just use the formula P equals e to the RT? Because we know that P is equal to P0 e to the RT, because we know that P0 is 1,000, and then E would be just the regular E, and then R is 0.05, that's the rate of growth.
Yeah, I'd rather you go through the process. In general, there's nothing wrong with the form, but I want you to go through it. It's usually required. Yeah. So I mean, we're not doing the departmental final, but the departmental final will usually ask you to show everything, and so I want you guys to be as good as the people taking the department final, at least. Okay, so now what? ln of both sides, because I need the t's in an exponential, I need to get it out, so I'm going to ln both sides. And what happens?
Divide by. Oh.
Right, ln and this cancels on this side, I will just have 0.05 t, so I can solve for t. T is ln of 2 divided by 0.05. Can someone tell me roughly what that is?
Is it 3.69?
Are you asking me? 3.69? Is that, did everyone get that?
Yeah, that's 30.8.
Make sure you try it on calculator, you should be able to get this. Don't want to go in the test and realize, I don't know how to use my calculator. Try it now. Right? Because in a test, I'll sometimes ask you to compute something in a calculator and say, do it to 2 decimal places, do it to 3 decimal places. So make sure you know how to plug all this stuff in your calculator. So 13.86. What's the unit of time here?
Oh.
That's what I was just about to ask.
Years.
Years. How do I know I'm talking about years?
Because
Because I said per annum in the original question. Per annum means per year, which means I'm thinking of years. Okay. Part D. How much money will you have in 6 years? How am I going to figure that out?
6 times.
Plug in 6 for time,
Yeah.
right? So this is just asking me for P of 6. which is going to be 1,000 e to the 0.05 times 6. And how much is that? This is now in dollars.
$1,349.85.
1,349.85. Did everyone get that? Yeah. So in 6 years, that's how much money we have. Any questions? Okay. Let's do a slightly harder situation. A woman gets 200,000 when she retires. Okay, that's her retirement package. She puts the money in an account. Again, very fictitious. You'll never see an interest rate like this in a bank account. But it's just to illustrate an idea. Earning 7% interest. The bank will never compound continuously, but whatever. Compounded continuously. This is applied on an annual basis. Okay. Okay. So now she's in retirement. She got that 200,000. She decides to put it in some account earning her 7% interest. But now she's not working, but she's going to be living off this account. So to live off it, she withdraws a certain amount of money per year. She withdraws and lives off of $20,000 per year. Obviously, she doesn't live in New York. Okay, A. Describe the balance in her account with an ODE. Initial condition. E. Solve the ODE. C. For how long can she withdraw her money? D. She wants to be able to withdraw for 15 years. She's like, there's no way I'm living past 15 years. No. You know, she's already pushing 70. You know, and no one ever probably lives past 85. So she's like, okay, this will probably last me for 15 years. She wants to budget. How much money should she withdraw per year? Okay, those are the questions. This is a pretty typical kind of problem. Guaranteed to see something like this on the first test and on the final. So you can make a note of that. It's coming. Okay, let's start. Describe this as an ODE.
So it says dp divided by dt equal to 0.07 p minus 20,000.
Minus
20,000.
20,000. Some students like writing 20 and then say it's in units of thousands, but I like writing out all the numbers. Initial condition? 200,000. So she's literally like almost withdrawing 1/10 of her money per year. How long do you think she'll be able to keep this up?
Like 20 years.
10.
Ah, if it was growing linearly, it would be around that, but it's not. There's an exponential growth happening. Let's see how much it actually can stretch the money. The fact that she's actually getting 7% interest being compounded continuously, let's see if she can stretch past that 10-year mark. So let's solve it. Yeah.
20,000 is K.
20,000 is K, yes. That's the amount she's withdrawing at regular time intervals, right? Every year she's taking out 20,000. So K is the amount being deposited or withdrawn. So her bank account is this, right? It's growing at 7% interest, but she's taking out 20,000 every year. Okay, so
You cross multiply the entire equation.
you could do that. One thing I know they like doing into a 9, I don't know. Because they always think that you guys will forget to do the substitution. They actually factor out the coefficient of the p. So in here you'll have 20,000 divided by 0.07. What number is that?
That's it's a long number.
Okay, what is it?
285,714.
285.
714.2857.
286. Let's do 3 decimal places because it's money, so we know it's 2 decimal places. So let's keep it at 3 decimals, and then we're going to round our final answer to 2 decimals. Yeah, so that's that. And now what they usually do is they divide by this guy. So we have dp over p minus 285,714.286 equals 0.07 dt. So we're going to integrate both sides. At this point, this side becomes what?
ln that stuff on the bottom.
ln of that whole thing on the bottom, right? And we don't have to worry about multiplying by a constant or anything like that, because if I do a U-substitution, the coefficient here is 1, my dp would equal du, which is why they like factoring out the constant. A lot of students would forget, if you move the whole thing over, you'd have to multiply this by 1 over 0.07. Which students forget that all the time, so they're like, oh, always do this, factor that. There's no reason that you have to. 0.07 t plus c, which means my p is equal to c e to the 0.07 t, and then this guy I'm going to add to the other side, plus 285,714.286. So that's it, right?
Do you think this method is better to factor out?
Yeah. I don't think it's better. Let me say it this way. People make less mistakes doing it this way. Are we done?
Nope.
Why not? Isn't that the answer?
Oh, for B, okay.
For part B?
Yeah, we're
We have initial condition.
We're not done. We have an initial condition. There's a C. We need to find that guy. So P of 0 equals 20,000 to 100,000, which means plug in T equals 0, I'm going to have 200,000 over here. 200, 1, 2, 3 equals C e to the 0 plus 285,714.286, which means my C is equal to what? Minus 85714. Right? And so now, finally the answer is minus 85714.286 e to the 0.07t plus 285,714.286. So that's the solution. This wouldn't be 286 here. What would that decimal be?
negative. Actually, it is.
It is
286.
200,000. This is 285,000. Okay. Okay. Yes. 286. All right. So that's our solution. You can kind of see where this is going, right? Nowhere good. Because here's a 285,000. That looks nice, but now we have an exponential attached to a negative, which means eventually this negative is going to pass that out.
Yeah.
So she's going to run out of money at some point, unfortunately. And I think part C asks us just that. Obviously, things aren't looking well here. How long will she be able to survive? How long can she actually withdraw money? How do I figure that out? How long will she be able to withdraw money?
Do you set up to 0?
Right. P describes the balance in her account. Right? P is the balance in the account. Right? It's the amount of money she has at time t. Right? So she can withdraw it until her balance hits 0. So for part C, that's what I'm going to solve for. 0 is equal to minus 85714.286 e to the 0.07t plus 285,714.286. And now I'm going to solve for t. How much time do we have? Which is, subtract this guy. Minus 285,714.286. You're going to divide by this guy. And you will have this guy. So what does that mean t is?
3, 3, 3, 3.
How would I get to the t? I'll end both sides because I want to get rid of that exponential. This side's going to do that. So t is going to be 1 over 0.07 times something times ln of this whole thing. 285,714.286 over 85,714.286. Okay, compute that in your calculators.
1.2039.
1 point?
I think I put something in wrong.
Yeah, that's definitely on.
That's not-
1 year, the first year.
She's done.
She withdrew $20,000 and she killed $200,000 in 1 year. I don't trust that banker.
17.1996.
17.19. Yeah, so roughly 17 years. Okay, so she actually stretched past the 10-year mark, right? So her bank account did help her out
Yeah.
a little bit.
Yeah.
Right? But part D, she expects to die 15 years from now. That's 2 extra years of money she could have spent,
Yeah.
you know, having fun in the clubs with the girlfriends and all that. Come on. She wants it to run out in 15 years. How much money should she be withdrawing?
The P equals all the money in Rome.
How do we set up that equation?
Just make T.
You want to set t equals 15? Okay, and what are we going to do with that?
So in the P equation,
What do we do with that? T equals 15. Great. How do we?
Start from the
You have to-
beginning.
Why do we have to start from the beginning?
Because that 20,000 is different.
Okay. The 20,000 being different affects what?
It's the ODE.
The ODE stays pretty much the same. What the 20,000 would change, we're changing the P of the K,
Yes.
right? Where we erased it. Okay, so what we're doing is we're changing the K, right? So this means our K, the amount we want to withdraw, is we don't know. That's exactly what we're searching for. So you go back to the beginning. You know that dp dt is equal to 0.07 p plus this k. Now this is the guy I want to find for the new situation, right? How much should she be taking out to run out of money in 15 years? Okay? My p naught is still the same, right? She's still retired with 200,000, right? But now she wants to know how much money should I be withdrawing at regular time intervals to run out of money in 15 years. So we are going to solve this now. So what do I do here? How do I solve that? What?
Just as you're doing it like in part A.
Yeah, so tell me what it would look like.
Okay, so we'll take the 0.07 out. Then we'll
Factor out the 0.07. Okay. What would I have left over in the brackets?
P plus K over 0.07. And then so I'll divide all that right there and multiply by dt.
P plus K over 0.07 equals 0.07 dt.
Then take the we'll down.
I want to ask because, you know, some people you replace a number with a letter. Oh my god, I joke. I was following you up to right there. Now, okay. So yeah. So again, we're doing the same process except now instead of a 20,000, we just replace the 20,000 with k, whatever it was. So we integrate this guy. We're going to get ln of p plus k over 0.07. Equals 0.07 t plus c. And so we have p is equal to ce to the 0.07 t minus this k over 0.07. Okay, now what?
Now that's it, just put the 15 for t and p is equal to 0 and then just solve. I mean,
We have
find
two
t
unknowns.
Find.
We have one equation, two unknowns. What do we do?
Can we figure out the P for C?
Find C. It's what we did last time. That's always the first thing you do. It's not done until you apply that initial condition. So we know that when time is 0, this guy's 200,000, right? This means 200, 1, 2, 3 is equal to C e to the 0 minus this k over 0.07. Which means my C would be equal to what? 200, 1, 2, 3 plus k over 0.07, right? Which means, finally my P is this monstrosity. 200, 1, 2, 3 plus k over 0.07 times e to the 0.07 t plus k over 0.07 minus k over 0.07. It's the minus here. Which makes sense. If your t is 0, this guy's gone. This kills that guy, and you're left with that 200,000. So now what? Now I can plug in the t and the p because I'd only have one other unknown to solve for, that k. Right? So I want to run out of money in 15 years. So when time is 15, I should have no money left in the account. And so now I'm going to solve for that k. Okay. Looks like a horrible equation. How do we solve for k? Exercise those algebra muscles. First step.
Add.
Add what?
Remove k to the other side.
This guy is separate. Add him to the other side. K over 0.07 equals 200, 1, 2, 3 plus k over 0.07. Is that what you do? If you're trying to solve for k, what should we be doing?
Couldn't you factor out?
You need k by itself on one side, right? So we went to a point where we had k's on one side of the equation. Now we have k's on two sides of the equation.
No, so you factor
We're actually
out.
taking a step backwards. I need to isolate k on one side of the equation. What do we want to do? What do we do? How do we get that k isolated?
Can also multiply by e to the whatever.
Right,
Yeah,
you expand the
you want
brackets. Multiply this guy out to break this k out of jail. So we have 200, 1, 2, 3, e to the, is that a nice number, 0.07 times 15?
1.05.
Let's keep writing that. 1.05 is this guy. Plus k over 0.07 e to the 1.05 minus k over 0.07. Now this is the guy that does not have a k in it. If I move that over. This is minus 200, 1, 2, 3, e to the 1.05 equals k over 0.07 e to the 1.05 minus k over 0.07. Now what? How do I get to k? It's a common term now. Just factor them out. So here I have minus 200, 1, 2, 3. E to the 1.05 equals k times e to the 1.05 over 0.07 minus 1 over 0.07. Which means ultimately my k is equal to minus 200, 1, 2, 3, e to the 1.05 all over e to 1.05 over 0.07 minus 1 over 0.07. And figuring out that from our calculator would lead us to the answer. Let's see if we can get a consensus on this. Are you sure this is a 1.05?
Yeah.
Okay. Get the calculator. Suspense is killing me.
It's negative.
Negative just means withdrawal. Don't worry about that.
To 21,536.
Two decimal places?
0.40.
Did everyone get that? Okay. So she should withdraw $21,536 per year. Right? Doing that under this situation, she'll actually run out of money in pretty much exactly 15 years, give or take a few days. At some point you'll see the process will be simple. The harder part is figuring out the algebra. Right? So you sort of know whenever you see a question like this, you know the differential equation that you're supposed to use. Right? So you're going to say it grows proportional to its size or it grows exponentially. It's being compounded continuously. You always start with that dp dt equals rt plus k. You'll always use separation of variables to solve it. You'll always plug in the initial conditions to solve for the c. The challenging part is really when they give you a situation, a scenario, and you have to plug in the numbers and go through the algebra to figure it out. That's where the challenge usually comes in. Any questions on this? On the idea?
How many questions will we have like this in the end? Or like,
Come in.
how many questions will like this will be on the
If a question like this is on an exam, I'll put 1. Yeah.
How many questions will be on
Maybe 5? 5-ish, 4-ish. Depends on the
For the entire.
We're like not even close to the exam yet. Why are you worrying about this?
We've been trained.
What's on the test? Is this on the test though? Do we need to know this?
No, I just wonder how much time.
Yo, facts, how many punches this guy? I was thinking that when we were doing it. Oh, that's lost that. 40 points or something, right?
No, this will be like a 15.
Oh, nah.
There's only 5
20, 15, 20 something.
Wait, how much time?
You're gonna need 3
15
days.
minutes per problem.
So 15 minutes per problem.
Let's go. Just one.
Jhevon?
Yeah.
On the syllabus, you said it says that we're going to practice Excel for homework. That we're doing that in class.
Not tonight. If we do Excel, do a few demonstrations, it would be on this. I show you on the computer what it would look like. So I don't have the equipment tonight, but we are, yeah, we're pretty much done with chapter 2 actually. So you can do the homework for that. The appendix for the Excel is in the back of the textbook. You can try that out. I feel like a lot of you would have used Excel already in research and stuff like that.
Yeah.
Yeah.
Hopefully you're familiar with that. Just play around with it. If you have any questions, I'll try to remember to bring a laptop next time and you'll see it. In the book, whenever they mention files for the Excel file, they're all downloaded from the Math 209 website. Right, so on the 209 website, there'll be a 209 files or Excel files. It'll be a zip file that'll have all the files inside it. Yeah.
So the chapter 2 homework is due a week from today.
Yeah, because we don't have class Monday. Monday's a holiday. So chapter 2 homework is on Wednesday. So we'll not do Excel. Probably try that on your own, and then we'll talk about it next time. We're moving on to chapter 3. It is entitled Numerical Solutions. So if you want to get technical, what we just did in chapter 2, you'd call those analytic solutions, right? These are solutions that you work out by hand and you figure out. Numeric are ones that you can't really calculate by hand usually, but you're doing approximations, right? You're actually plugging in numbers and doing approximations to get to an answer. In general, differential equations, they're actually pretty difficult to solve. In the majority of times in nature, we won't know how to solve them. There will be, oh yeah, it's just a nice separation of row. That almost never happens. So sometimes your ODE looks really complicated and we don't really know how to actually solve it. And so what we can do is we can use what's called numerical methods or approximation methods to get to solutions. So we call this numerical solutions to ODEs. And we are going to use our knowledge of tangent lines to get through this. Love tangent lines are awesome. Okay. Just a little intro blurb. Here we'll learn how to approximate solutions. Right? Things that we can't find exactly by hand, so we kind of try to get as close to the answer as we possibly can. One of the biggest difference between approximating solutions and finding a general solution analytically is that approximations only work at a point, right? They're approximations because you don't know how to find the function that solves it in general. But if you know where you want to be at a certain situation, at a certain point in time, what's going on, right? You don't know what's going on in general, but at a certain point in time, you want to know what's going on. You can use a numerical method.
Like the tangent line of a curve?
Like in the tangent lines of a curve, and you're extending it to a certain point. Provided certain conditions, you'll actually get something pretty close to the answer. And we'll actually do some things by hand in our calculator and using these methods, and we'll see that, hey, it's actually not far from the answer. You'll see it's pretty cool stuff. Okay. So before we know how to approximate ODEs, let's look at approximating normal functions, right? Someone already released the spoiler. Tangent lines is the big idea here. So here's the idea. Right, so this is the idea. Illustration of the idea. Okay. So we have this weird function, right? Doing something. Right? Don't know what it's doing. I don't know a formula for this function. It's very difficult for me to find a formula for this function. Right? What's not difficult is find the formula for a straight line. If I know the point and the slope, I can find the equation of any line pretty easily. Right? So what I want to do is let's say I know some initial condition, right? So at some point x, I actually know what the value of this function is, right? So this is f of x, right? But I don't really know what the function is doing otherwise. It's very difficult for me to find it. But at this point, I know a lot of information about the function. I sort of even know its differential equation. Now, remember, the differential equation has a derivative in it. The derivative is telling me the rate of change, which means I have the information that tells me the slope at this point also, which means I'd be able to find a tangent line. So in theory, I have this function, don't know what it's doing in general, but at a certain point, I have a lot of information. I know its value, and I know how it's changing because I have that information from a differential equation, right? So it means I'd be able to find a tangent line to approximate the function. Now, x is some point in time. Now I'm wanting to predict in the future, like what it's going to be at a certain value, right? So over here, let me put x plus delta x. It's the notation your book used. A change in x is delta x, right? So at delta x time in the future, right? Some change in this time. I want to know, what is the value of the function at this point, right? I don't know what the heck the function is, right? So it's hard for me to tell that, but I do know the equation of the tangent line. That's easy to find. So instead what I'm going to do is I'm going to go up to the tangent line, and that's going to give me a y value. So this will be the y value. This guy here, since this is f of x, this is f of x plus delta x, right? Now that's the actual value of the function. That's what I want to know, but I don't know how to figure that out, right? So what we call is this distance here, the difference between the actual value that we had from the original point to the new point, that distance is called delta y, the change in the y value. The distance between the slope, the tangent line, the derivative of the function, and the original value, that we call dy. That's what your dy is. Right? So dy is like an approximation of your change in y. So the idea is this. The closer we are to this, the difference between the line itself and the tangent line is not going to be that big, right? It might deviate further as we go off, but when you're just here, like right in this neighborhood here, like a very small window, the difference between the tangent line and the actual function is not going to be that much. It's going to be super small, right? So the idea is we want to figure out how to make this approximation in a super small window to approximate the function. So we will actually get here, this is y plus dy, right? Which is going to be our approximation of this value. Right? So I want to figure out what this y value is, but I don't know it. So I approximate with the tangent line. The closer the point is to where the original point is, right, the smaller our delta x is, the better our approximation will be. This gap will actually close. Okay? So that's sort of the idea. We're sort of going to use a tangent line to approximate a function. You'll never have to explain this theory, but I wanted to explain it so you sort of see in the background what's going on. Okay, so let's look at this. I'm going to derive this formula for you that we're going to be using. I should probably mention that. Provided delta x is very small, the difference between delta y and dy is also very small. And so the idea is I can use this value to approximate that value and hence figure out what the function is doing. Okay. So let's look at this. Now, if I look at the derivative of this function, right, let's figure out what the slope is. Slope is rise over length. Right? So I want to figure out the slope of this tangent line. What's the run between this point and this point?
X.
Delta x, right? Delta x. What is the rise?
Delta y.
What?
I'm looking at the tangent line, not the function, right? I want to find the slope of this line.
dy.
It's dy, right? So I move, run is delta x, the rise is dy. This means my dy, I can actually compute it. If I know the derivative at that point and the distance I'm moving, my dy is actually given by that formula. Now, what's our new y value? It'll be approximately the old y value plus the change in y, right? Well, it's actually exactly the same. This will approximate by the old y plus dy, right? I don't know the actual change in y, so I'm going to pretend I can use dy to approximate that. If my delta x is small enough, that would work. So this means new y is equal to old y plus dy. But I know what dy is. And I actually know what new y is as well. Hence we get, and by the way, this is actually numbered in your book. I should probably in your textbook, this is referred to as theorem 3.1. If delta x is small, and we know f of x and f prime of x, right? So here's a function where I know a value at some point and the derivative at that point. We can approximate the new y value. The new y value is f of x plus delta x by the following. F of x plus delta x. Here's a summary. This is what you need to remember. Is approximately equal to, right? This is our new y value. What is it approximately equal to? The old y value. The old y value is f of x plus the change in y, which we're approximating with dy, which is f prime of x delta x. Now this is actually a formula that you've seen in Tool 5 before. It might have been using different notation. They might have used a, f of x minus a as something like the delta x is the same sort of idea. We might use different notation here, but it's actually the same formula. It's called the linear approximation formula. Right? Basically approximating a function using the tangent line. And that's sort of where the idea comes from. They figure out what the dy is, they replace the change in y with dy, and we derive that formula. Right, so this formula is very important. This you have to memorize. Right, so I'm not going to give you a formula sheet. You have to, this is just something you know now. So that you memorize. Okay, let's actually use this formula. See this guy in action. See how good it actually is. Use theorem 3.1 to approximate the following. The radical of 25.1, the radical of 25.05, the cube root of 7.9. Let's see how good this guy actually is.
Don't we need other values? Like,
I know.
aren't we supposed to have givens?
You tell me.
Yes.
How would you approach this problem? Radical of 25.1. Obviously, to apply this method, I need to know some sort of function to work with, right?
It's very tough.
Yeah. What do you think is a function that I could use here?
F(x) equals radical x.
F of x equals radical x, right? Notice, we want to approximate what value?
25.1.
I want to approximate f of 25.1. Okay?
We know 25.
So this, we know 25. This is like my new y value, this value that I don't know, that's so elusive, right? This is like my x plus delta x, right? What do I need though? I need to know what the value of a function is at a certain point and the derivative at a certain point, right? What point do I know the radical of that's pretty close to 25? 25, okay. We know f of 25, and you bet that we know f prime of 25, right? Because I know my f of x, I can find the derivative, plug in 25. 25 is a nice number. Things will work out really nicely, right? It's the 25 that 0.1 really killed us, right? So here, let's actually start to replace some of our variables, right? Like, what is our x? What is our delta x?
X is 25.
X is 25. That's the number we know, right? We know what the value is at 25 and the derivative. What's our delta x, the change in x? 0.1, right? 0.1 is our delta x, that's our change. We started at 25, but we increased by 0.1. And I want to know if we increase by 0.1, what is the actual difference, right? Okay. So let's get to this. In our formula, we need to use the derivative. So let's start there. F of x equals radical x, right? And we know that f of 25 would therefore be radical 25, which I know is 5. No problem. Okay, what's our derivative?
25.
1 over 2 radical x, right? So what is the derivative at the nice point that we know? 1 over 2 radical 25, which is going to be 1 over 10. This means that if I take radical of 25.1, this is actually f of 25.1. This is approximately equal to f of 25 plus f prime of 25 times our delta x, which is 0.1, right? This is like my x plus delta x. This is my f of x. This is my f prime of x. This is my delta x. Just plug into that formula. Figuring out what are the nice numbers that I know. That's my x. My delta x is the distance that I move to get to a new number. F of 25 is 5. Plus f prime of 25 is 110. Times 0.1 is also 110. Right? 110 times 110 is 100th. So this is 5.01. Right? This is my approximation. So the radical of 25.1 is approximately 5.01. Is that a good approximation? What's the actual answer from the calculator? 5.0.
0 again. 999.
99999.
What did you
Which,
I lost you over there.
which part?
At the end, so you
Do we have here the formula? You get that? You plug in the x, which is 25, plug in your delta x, which is 0.1. f of 25 I found earlier, it's 5. F prime of 25, found that earlier, put that in. 0.1 I just wrote as a fraction, because I was computing in my head, it's easier to do it that way. So this is 1 over 100, 1 over 100 is 0.01, plus that 5, I get 5.01, right? Now 5.01 is my approximation of what this guy is.
Okay.
Now I ask, what is the actual answer? Right? Like, if you plugged it into a calculator and we didn't do this by hand, what would the actual answer be? And someone plugged it in and they got 5.00999. Now my approximation was good up to 2 decimal places. So if I round this to 2 decimal places, what do I get? Number right before the second decimal place is bigger than 5. This gives me a 5.01. To 2 decimal places, I got the exact answer. Not too shabby. Yeah, if you're ever stuck in the wilderness and there are no calculators and you need to find the radical of 25.1 to save your life, you could do it. Yeah, it's 5.01. Yes?
All the way, like in the corner, you have, then times point one. Well, you're doing
Right, this is f of 25 plus f prime of 25 times 0.1.
and that's your delta x.
The 0.1 is my delta x. The 25 are my x's. Okay? Let's do it again. We're going to do it 3 more times so you sort of see how this thing works. Let's do 25.05 and see how good our approximation using theorem 3.1 is. Right, so now we want to know 25.05. What's my function? Same one, it's the radical of something, right? And I want to know that something, so I'm going to think the function is radical x, which means f prime is 1 over 2 radical x. It's still a good idea to make x equals 25, right? Remember, we want the gap to be small, so we want to choose a value that's very close to this one that we already know the answer for, right? 25 is pretty close to 25.05. It's the closest number to 25.05 that we do know the radical of. So I'd still take that 25. What is delta x? 0.05. So at this point, I'm going to want to know the value at 25. F of 25 is 5. At this point, I'm going to want to know the derivative at 25. You computed this before. This was 110. Now, I'm going to plug that into my formula. This means the radical of 25.05 is approximately equal to the value at 25 plus the derivative at 25 times the change. What's the change here? 0.05. So this guy is 5 plus this is 1 over 10 times 1 over, what's that? It's like 1 over 20, right? Which is 1 over 200. 1 over 200 is what? Give me as a decimal. 0.005. Actual answer. The radical of 25.05 in your calculator is
5.0049.
rounded to 3 decimal places. Right? I was off by 0.001. Right? I was within the answer by 1,000th. So now you're sort of seeing the power of this technique, right? I don't actually know what the function is doing, but I'm guessing based on what the tangent line is doing, and I'm actually getting it pretty close. Right? But Jhevon, we actually know a formula for the function. Hold your horses. We'll get to the point where you don't actually know the formula. Just want to know that you can crawl before you walk. You know? do this once more. Let's approximate the last one with the cube root of 7.9. 7.9. Let's approximate that. Using theorem 3.1, we're going to need a formula to work with. Cube root of x seems to make sense to me. I'm going to approximate the cube root of something. Okay? Now, thinking of that, what would my x and my delta x be? Tell me a value close to 7.9 that I know the cube root. 8. Super close to 7.9, I know the cube root. What's my delta x?
0.1.
Negative 0.1. Because to go from 8 to 7.9, I decreased, right? I moved it to the left by 0.1, right? So now I know the value of the function here, which means f of 8 is actually 2. Find the derivative. What's the derivative of this guy?
Negative. Underneath.
What?
Cube root x squared
In the bottom.
on the bottom.
Cube root of what?
X squared.
X squared, right? You can think of this as x to the 1/3. The derivative is 1/3 x to the minus 2/3, which when you write it as a radical, you get this. So this means f prime of 8 equals 1/3 times cube root of 8 is 2, but I square it, right? And so that's 1/12. And so now I can do my approximation because I know all the pieces I needed to know. So the cube root of 7.9 is approximately equal to f of 8 plus f prime of 8 times my delta x minus 0.1. F of 8 was 2. F prime of 8 is 1/12 times minus 0.1. What's that? It's 1 point something, 1.9 something maybe. $1.99. 1.99 what? 1.6. Okay, let's do 4 decimal places. 1.9916. Actual answer. Cube root of 7.9 is 1.99. 163. What was the number after here? 6. It was another 6. I was off by 0.00003. Look, Mom, know what happens. Didn't even need a calculator. Oh, technically did, sorry. Whatever. So you get the idea. So our function is doing something, don't know exactly what it's doing, but I can use the tangent line and this formula to sort of approximate what it's doing. And that is super powerful. Now I know it sort of seems like we're cheating because here we actually know a formula for the function, but come next time I'm going to teach you something called Euler's method. That's going to help you to do approximations when we don't even know what the formula for the function is. And we're going to use this to solve ODEs and approximate them at a point. So chapter 2 homework is due Wednesday. Chapter 3 we didn't finish, so nothing there. We'll pick up with Euler's method next time. Try the Excel homework on your own, and we'll ask questions next time.